All right, so I guess these are kind of less of example problems than they are just cool applications of the circuits that we're looking at. For the, op amp summer, I formed it as a question to design a circuit that takes the average of 3 input voltages, but really just wanted to demonstrate that you could use these circuits to, pull an average of 3 input signals. Similarly, for the op amp integrator configuration, I'm going to show you how you can use it to configure a triangle wave generator. So basically a circuit that will output a triangle wave output with respect to time. So this would be my voltage axis, and this would be my time axis, right? And my output voltage would be a triangle wave, and that can be created using an op amp integrator. So let's go ahead and draw my op amp integrator and draw it just like this. And what I would have to do is I have to do a pretty clever switching scheme on the input. So this will be V out of T. This will be my C, and this will be my R. And of course, what I'm going to have to do on the input side is pretty complicated, but bear with me. I'm basically going to have let's see how to do this. What's the best way to do this? I'm going to go ahead and put 2 voltage sources connected as such. And then each one will have an associated switch. Okay? And so what I'm going to do is I'm basically going to let this one be on for every other millisecond, and then this one be on for every other millisecond. So basically, we're going to put 5 volts here and 5 volts here. And so what happens when this switch is closed is my input is 5 volts. And what happens when this switch is closed, then my input is negative 5 volts, right? And that's assuming that they are non-overlapping switches. That basically means that one will be open when the other one is closed. So we'll never have the case where they're both closed at the same time, because that would violate all the laws of KVL, and we would have all kinds of problems if that were the case. So let's assume for this problem that anytime I close the blue switch, then the green switch opens, and anytime I close the green switch, then the blue switch opens. Okay? So if I were to do that, then what would happen? Let's see. Let's go case 1 would be the blue switch is closed. And what would I have? I would have that. Let me look at my previous slide. Let me go ahead and grab this. I would have V out is equal to negative 1 over RC times the integral from 0 to t of V in, which would be negative 1 over RC times the integral from 0 to t of 5 volts dt, which would give me negative 1 over RC times 5t for V out of t. Okay? Let's say each switch is on for 1 millisecond. Oops. 1 millisecond at a time. That would mean that each transition here would happen in 1 millisecond. And so this first V out of t is when my blue switch is on. So I'll just draw like a blue little line here, and then green, and then blue, and then green, and so on. So when my blue switch is on, I can see that I'm going to have a slope of negative 5 over RC, right? So this slope here is negative 5 over RC. Well, what's going to happen when my green switch is on and my blue switch is off, or my green switch is closed and my blue switch is open? That's going to be green switch is closed, Again, we're not assuming that there's ever going to be a time where both switches are closed at the same time, because that would violate rules. So in this case, I would have V out of t is going to be equal to negative 1 over RC times the integral from 0 to t of negative 5 volts for the green switch. Of course, that's what I have here, dt. And I would get 1 over RC times 5t. So I would end up with V out being positive 5t over RC, and my slope in this case would be positive 5 over RC, and so I would end up getting the opposite case where this starts rising with a slope of 5 over RC. And then again, 1 millisecond later, when the blue switch closes, I would go back to negative 5 over RC for my slope, and so on forever. And this would generate a triangle wave at the output. Right? Okay. And we would have to just make sure, of course, that this amount of time that the blue switch on and the green switch are on are equal. Let's call it T1. And I think that I said a couple times, let's just assume that it's 1 millisecond on, 1 millisecond here, 1 millisecond here, because if we didn't, then what would happen? Well, if one of those situations, if one of the switches is on longer than the other one, then we're not going to get something that's got a constant average value. We would get something that would run away, because one would be on for a long time and then the other one would only be on for a short time, and then one would be on for a long time. And so this would run away, and we would eventually get either a positive or a negative infinite voltage, and something would blow up in our circuit. So if we were going to ever design this circuit practically, we need to make sure that our switches, A, are never on at the same time, and B, when they are alternating, that they alternate at the same rate. That when the amount of time that the blue switch is on would be the same as the amount of time that the green switch is on, in order to prevent that runaway scenario. Okay, so that's how you design a triangle wave generator using an op-amp integrator. And we are officially done with pretty much everything having to do with op-amps in this last slide. I think I actually left myself one extra triangle wave slide just in case I needed it, but it doesn't look like I'm going to need it. So in the last slide here, I'm going to talk about one final big practical implication or practical limitation of op-amps, and then we will move on to the final section of Module 5. Okay, going to go ahead and end this video now.